Hello everyone, Jim Malos again. Let me talk to you guys a bit. We'll see what we can do. Let's talk about Chapter 6 and some of the problems I was trying to do related to that. What we are looking at for that will be, let me just make sure everything's functioning okay here, guys, as I do this. Okay, looking pretty good. See a few things here. What we're doing is for Chapter 6, I'm going to look at problems 20, 35, 41, and 67. And let's see where we are vis-a-vis all that. Start with 20. So for problem number 20, they are saying a sled and rider have a mass of 56.8 kilograms. They are at rest on a snowy hill. The coefficient of static friction between the sled and the snow is 0.225. What is the maximum angle of the hill slope measured upward from the horizontal so that they stay stationary, you guys, is what they're trying to say there on that one. I touched on this a bit at some other point. So let's kind of proceed from there. We're saying, let's make it look like this. This is theta. And let me, not liking my chalk too much, guys. Let me see here. All right, let's try. Go back and forth with some of the chalk, I guess you could say. We're looking at something like that. And there's going to be a frictional force that way. There's a normal force that way that's equal and opposite to something going on over here. The something going on over here is, well, there's another, I guess you could say there's a number of ways you could look at that. This guy going straight down, that's mg. And this guy right here, now let's be careful. If this is theta, and this is 90 degrees, and this is 90 minus theta, and the whole thing is 90, once again, you're back alive with theta. That's always going to be the case in this kind of a triangle. If that's the case here, this is mg cosine theta. This is mg sine theta. Not bad. Okay. Something to kind of look at that way. This guy is equal and opposite. This is the normal force. They write it like this sometimes. I wrote it as capital N one time. I'll kind of defer, at least in this problem, to kind of the way you often see it written. See it like that. M equals 56.8 kilograms. M sub s is 0.225. See here, for some reason I'm kind of putting the carriage in front of the horse on this whole thing. I wrote a whole bunch of answers here. Let me write it here. Let me kind of figure out where we're going to go with it. For some reason I'm having an issue here. Oh, the angle of the hill slope measured upward from the horizontal is this. Are they at rest? Well, let me see here. Was that that was 20? I didn't want 20. I didn't want 21, rather. I wanted 20. Let me see 20. That's not a big deal. I can still. Okay. I don't. Please let me take that back, or maybe not take too much of that back. We still got the 56.8 coefficient of kinetic friction is what it is. There's a number of ways you can write it. I wrote it this way in the notes that I have for the particular problem. It's written a little differently. That doesn't amount to anything, guys. Not really any big thing here. There is a slide down potential, I guess you could say, a weight component, W sub x, that kind of gives it the potential to want to slide down. The frictional force has got to be at least equal and opposite to this slide down potential, as they say. Everything else is set up right. When you look at my notes, the orientation of the triangle, is going to be a bit different, but that's nothing. That doesn't really mean anything. So when you got all this, the frictional force, well, let's talk. The normal force is this. I sometimes write it like this. I've seen it written different ways in different literature. The frictional force is going to be mu sub s, F sub n, looking like that. And that's got to be equal to the slide down potential, if you allow me to say that, kind of the tendency to slide down, and that's mg sine theta. We've kind of gone down this path in the past. So F equals W sub x, and so we can basically go a lot of ways on that. I mean, if that's the case, you got mu sub s times F sub n is equal to mg sine theta. Okay, so all right, that's from all this right here, we really come right there, and right there just means this. Just look at how I got everything labeled up there, and you should be okay. Well, okay, that's fine. What's the normal force? The normal force is mg cosine theta. So that guy's mg cosine theta. So let's keep writing, I guess you could say. M sub s, forgive me here, M sub s times F sub n. F sub n is equal and opposite to the weight component going down, so it's equal and opposite to mg cosine theta. So mu s times mg cosine theta equals mg sine theta. So there it is. I mean, that's a pretty big move here. I mean, we have been kind of tinkering with this all over the place. I mean, this right here is let me not say that actually. No, that's actually true. And this guy right here was mu sub s mg cosine. Let me give myself a little bit more room, guys. Mu sub s mg cosine theta. Mu sub s mg cosine theta. This guy right here, looking good. So we're over here, guys. If you're over there, just do some math and let's figure out where we're at. I mean, at the end of the day, let me divide by mg cosine theta on both sides. Well, I mean, there's a lot getting canceled out there, you guys. At the end of the day, you're getting this. And at the end of all that, you're getting this. If that is the case, let's solve for theta. Theta is going to be the inverse tangent. Do the inverse tangent on each side. Do the inverse tangent of tan theta, you get theta. Do the inverse tangent of mu s, and you get, like I said, inverse tangent of mu s equals inverse tangent of tan theta, which is theta. Theta equals the inverse tangent of mu s. They gave us, again, watch the units. Make sure units are fine, guys. I cannot be If you make a mistake, I mean, like I said, if an engineer makes a mistake building something and people get hurt, they say, oh, wow, I knew what I was doing, but my calculator settings were wrong. You're still wrong. I'm still wrong when I make that mistake. Anybody's wrong, and then the consequences are definitely wrong. So you got to make sure things are going right, okay? You got to make sure you have everything set up as it should be, and you're using the technology correctly as well. That's part of the process. That's part of the process for which we're held accountable. So you look at it, they're telling us the coefficient of static friction is 0.225. So you put that here. At the end of the day, this is the maximum angle. Make sure if you're dealing with radians, you convert them to degrees, unless they ask you to give it in radians. The question will be clear what they're asking. You just got to make sure you answer the question. This guy's the maximum angle. Looking pretty good. It's looking all right. I mean, that's what they want to say for 20. Let's go to 35. There's a lot here for 35. But that's okay. We can do it. We're going to do it fine. Kind of a lengthy presentation because the question itself is a little bit on the lengthy side. But let's take a look at number 35 from chapter 6 and see what we can say here. Let's read it. Let's go for it. For number 35, chapter 6, the Katz book, a small sphere of mass m equals 0.5 kilograms is dropped from rest into a viscous fluid in which the resistive force on the sphere can be expressed as F sub d vector equals negative b v vector, and reaches 1/4 its terminal speed in 3.45 seconds. A, what is the terminal speed of the sphere? Terminal speed is the speed at which it can go no faster, ladies and gentlemen. B, what is the distance traveled by the sphere in those 3.45 seconds? It's a nice question. Definitely a calculus type problem. Definitely a calculus type problem. All right, so let's take a look at it. Leave this like this. Let me kind of just go around this thing. Okay. Let's take a look. Let's see what we can see here. Try to maximize. Sometimes I got to erase all this stuff, guys. Sometimes I'll just try to leave it up there as best I can. It is a fascinating problem. Let's talk about it. They say what they're trying to say here. If you have reached a terminal speed, what is going on? What is going on when we've reached a terminal speed, you guys? Well, there's a lot going on. I mean, if you reach a terminal speed, it's not speeding up anymore. It's also not slowing down. When something's moving at a constant velocity, there's no unbalanced force on it. The forces are equal. Let me just put it that way, in a very kind of generic sense. I mean, there's more that can be said, I guess, but for our purposes, let's take a look at what we just said. I mean, you're looking at a situation where how do you want to look at this thing? How's this thing playing out? Well, I just told you, if it reaches a terminal speed, nobody's got the upper hand on this thing. It's kind of a stalemate. If there's a terminal speed, there's no acceleration taking place. No speeding up, no slowing down. Terminal speed. The forces are balanced. What does that mean? That means the drag force, F sub d in terms of magnitude, is equal to the force associated with gravity. They are equal. Now I know the way they write this thing. I mean, the way they wrote it in the book. They're saying F sub d vector equals negative b v vector. Absolutely, it's valid. What does that mean? Negative b v vector. That's F sub d vector. This is absolutely true. Nobody's debating this. It's negative because it's going to stop this thing. It's a force that's going to, it's sort of like friction. It's going to oppose the motion. This thing right here is going to, it's going to oppose any kind of motion that's taking place to the point where it's just going to bring it right down to, make a dead heat there. There's a constant velocity going on. It's going to reach terminal velocity. Well, I'll tell you what, how big is this force? Negative b v vector. F sub d vector is negative b v vector. How big is that force? That force right there is as big as bv in terms of magnitude. The weight force is as big as that. What does that mean? Well, that means when they are equal, there's a terminal velocity here. And the terminal velocity is that. Okay, that is what the terminal velocity is. So from there, I guess we can figure out a whole bunch. Kind of keep it in our mind. I will say, and here's where you got to be pretty slick about the whole thing. Before there is a terminal velocity, there's a velocity that is smaller. And the velocity is constantly changing, constantly getting bigger until it reaches the terminal velocity. Before it reaches the terminal velocity, there's going to be an acceleration. What do we mean? Well, then we say mass times acceleration is the unbalanced force. mg is the thing driving the whole thing, and it's being slowed down according to minus bv. If you divide by m on each side, you're down here. Isn't acceleration dv dt? Using our calculus background. Okay, yeah, sure. It's good enough for me. I see that. What do you say? You take all of this right here and divide it on both sides. After you do that, multiply by dt on each side, and you end up getting this. G's a constant, B's a constant, M's a constant, V's the only guy varying. Okay, so it's not as scary as we think it is. You can't say it's completely non-intimidating, but this, G is a constant, B's a constant, M's a constant. Here's V. You divide by this quantity on each side, got a 1 left over, then you multiply by dt on each side. 1 times dt is just dt. Having done that, let's see what we can do. I mean, we got it to here. Got it to here. So let me see what I can say. If these two are equal, when you integrate the right way, you should be okay. If these two are equal, the appropriate integral on each side remains, the reality remains that there's an equation still. There's an equation right now, right here. Equation right now. When you integrate each side, you still have an equation, if you do it right. So you go here. You got this. I'll integrate over here. Okay, now we got to be careful. Yeah, that's true. I mean, I guess we started at 0 velocity and we got up to a max velocity somewhere, or we got up to a velocity, some velocity v. And we got up to v. How did we do it? We got up to it from time equals 0 to time equals t. Pretty generic, but it's very true. When we integrate, that's its own kind of fascinating thing right here as well. This has got the logarithmic function written all over it. I told you that the exponential function, you guys, is probably the most important function of all of mathematics. Its inverse is born, I guess, from the exponential function. Its inverse is the logarithmic function. E to the x and ln x are inverses of one another. The natural logarithm, ln x, and e to the x are inverse functions of one another. Extremely important. One's born of the other, as we said. ln is, I think, logarithmus naturalis. Logarithm natural. So they just call it ln. Very special function. We can convert every logarithmic function to any other logarithmic function. We can convert every exponential function to every other exponential function. But man, e to the x and ln x really have some special, right off the bat, they're kind of similar to what I was saying about the radians, how important they are and how they occur all over the place, right? It's looking like that. How are you going to integrate this? Well, the integral of dv over v is ln v. This is kind of sort of like that, but it's this guy right here. How this thing's going to integrate is going to be ln of this entire mess times negative m over b to actually get there. So it's negative m over b. You integrate this thing, it's going to be negative m over b when you grind out the integration. Negative m over b times ln of g minus b over m v. And that is going to be evaluated, ladies and gentlemen, from 0 to v. The other one, let's just make sure that was on the mark. Basically, you got to call this guy a u and say, well, how would I do this? Well, if that was a u and how it all plays out, it'd be negative b over m dv. Well, I don't quite have that, but I can put negative b over m dv, but cancel out by a negative m over b to have it work out. Anyway, there's a whole bunch of processes to get there. We can do it. When we do the integral, when we do this integral, we are getting this. We do this integral, we're getting something pretty easy. It's looking like this. Well, when you evaluate this thing, you put the v here, and yeah, it looks good to me. And then the other way, you put the 0 here. 0 times here is just ln g. So what we got here, guys, is negative m over b ln g b over m v minus, put the 0 right here, b over m times 0 is 0, that's just ln g. That's ln g. Don't need, this guy's on the outside, so he's hitting everybody when we're doing this whole thing. So that's fine, nothing wrong with that. And we got a t right here. Now, you guys know that the difference of two logarithms is the logarithm of the quotient. So it is coming out something like this. ln go right here. Alrighty, let me see here. Try to use various chalk here, guys, to kind of conserve the chalk. I got to try to use some good chalk for you guys to be able to see it okay. We've got this. And let's see, probably overdoing it right here, but let me do it anyway. So we got that right there. We got ln g. We got the g right here. And that's equal to t. And that's equal to t. A number of looks we could give this thing, guys, if you wanted to do it, if you want to pull it off. What do you say you multiply by the reciprocal of this quantity right here. Multiply by the reciprocal of this guy on each side. Multiply by negative b over m on each side, and let's see where we are. Okay, again, guys, I can erase a whole lot more than maybe I normally would even. That's maybe the one small advantage we got in this whole process, I guess. You always go back with the film. You can see this stuff. See what I can do here for you. Got it to here. We got all that. I said multiply by negative b over m on each side. Let's see where it goes. We have ln over G. That's that. Sounds good to me. What do you say you exponentiate each side? What do you mean by that? Well, I got this right here. Everybody see that? We got it right here. We got it right here. If two things are equal, okay, these two are definitely equal. If these two quantities are equal, they remain equal if you exponentiate each side. Basically, if you exponentiate the logarithm of a quantity, you just get the quantity. The exponentiation of the inverse of the function of exponentiating, which is taking the logarithm, the exponentiation of the logarithm of something, is just the something. And this right here is e to the negative b over m times t. Okay, we got to here. Now what? Well, what do you say we try to make some sense out of this thing as we got it? What do you say you multiply by g on each side? Multiply by g on each side. Sorry, that would be v. Forgive me, guys. I forgot the alphabet the last day or so. All right, so we're here. You got it up to there. What do you think? Well, okay. I mean, it's okay. I mean, but let me see if I can start knocking stuff out left and right here. What do you say I add a positive b over mv on each side and then subtract this quantity right here on each side? When you do that whole song and dance, you end up getting this. You end up getting, so I'm going to add a positive b over mv. I'm going to add a positive b over mv on each side and then subtract g e to the negative b over mt on each side. And that's going to come out to, you horse around with this thing a little bit, and you should be all right. We come out to here. There was a v right there. Sorry about that. And that g, factor a g out of there. Okay. Not too bad. From here, start erasing a few things here, guys. Okay, we are here. We got it to here. Multiply by m over b on each side. Not sure what's going on with this right here, guys. Multiply by m over b on each side. That mg looks awfully familiar. It's the weight. Kind of neat how that works out. Multiply by m over b on each side of the equation. And we got well, here's a formula for you guys. There's a formula for us. And that's where it's coming from. That's what V is. So there's a formula as to how this proceeds to get to where you're going to go, to find this thing working, guys, as it's going to go. All right. Not sure what's going on with this chalk, guys, but if you guys can see that okay, let me get a good view here. I think we're okay. We should be fine. Yeah, looks fine. All right, so if that's the case, now they just want us to figure out how that's going to happen, how that actually got there. So there's a lot we can do. I mean, what they're trying to say is, you got to remember, this tells us a lot. Plain and simple. This whole thing tells us an awful lot. And certainly tells us a lot, guys, and I just got to tell you a couple things on it. I got it in the notes too. Remember, in this entire song and dance, we started right here. Mg, well, we derived up to here. Mg over B is equal to V sub t. And they tell us that T equals 3.45 seconds. They gave us some information. T equals 3.45 seconds, and V is 1/4 V sub t. So let's talk. The way this is spoken, they're telling us it reaches 1/4 its terminal speed in 3.45 seconds. What is the terminal speed of the sphere? What is the distance traveled by the sphere in 3.45 seconds? So T was this, V was 1/4 the terminal velocity at T equals 3.45 seconds, we've got this. At T equals 3.45 seconds, we have 1/4 the terminal velocity. Put another way, at 1/4 the terminal velocity, we have T equals 3.45 seconds. All right. So if you're using this formula, guys, that we have up here, very important. We got it here. What about it? We have the following. We can do a lot of work to get there. So what we have is again, we're doing the whole process just fine. Okay, we know this, so we're going to figure out what we're going to do for A, how we're going to actually make it happen. Well, again, the real big, this is it. This covers the whole show, you guys. Simple as that. This is V. The V under consideration is, let's use the data that they gave us. There's no point in trying to, we've got some general conclusions. We've had general conclusions from the beginning of this problem. Good general conclusions. I mean, they told us this, and from there we played the games that we could play to actually find out where we are. We figured out how you're going to actually find this, what's going on, and basically, the guy kind of started the whole process was we had MA is equal to MG minus BV. And from here, we just started, the process was that's dV dt, A is dV dt, mg is mg, a constant, m and g are constants for our purposes, b is a constant, v was a variable, and from here it was this differential equation that got everything rolling. That got everything rolling. That differential equation got everything rolling. So there it is. Well, if that's the case, this differential equation, when we did all the work on it that we had to do, when we did all the work that we had to do with this particular differential equation, we drew a lot of conclusions and we culminated right here. Any V you want to put in there, if they're already telling you what T is, you might be in good shape. There's another thing that's really of interest. Terminal velocity was that. We figured that when the forces were equal, when you reach the point, basically when you reach the point that BV was equal to mg, you divided by B on each side. That was the terminal, and that's something we've already concluded as well. That's something we already concluded. Wait a minute. This, mg divided by B is VT. V is 1/4 VT in this circumstance, and they gave you what this is. I think we're doing pretty good. I mean, if they tell us something like that, I think we're doing relatively well vis-a-vis something like that. So to find B won't be too much of a problem. Basically, what I'll do is I'll put in for that equation way up top, way over there. For V, I'll put in this. For mg over B, I'll say this. That's just the mathematics. Okay, we're looking at that. Let me divide by VT on each side. Let me divide by V sub t on each side, and let me just keep going here. What's my goal? My goal is to find B. My goal is to find B. The rest is math. The rest is math. You've got to think your way through this. You can't make a mistake, obviously. I mean, one mistake somewhere along the lines almost always means the whole thing's going to get wrong at the end. See what I can do. Let me add a positive e to the negative b over m times t. Let me add a positive e to the negative b over m t. on each side, and let me subtract 1/4 on each side after I do that. Fair enough? Well, so we have this. E equals negative b over m times e to the negative b over m times t is equal to 3/4 or 0.75. Take the natural logarithm. Logarithmus naturalis, as they say. Take the natural logarithm of each side. Take the natural logarithm of each side, multiply by, you can do this, play this a whole bunch of ways, guys. Look, at the end of the day, guys, we're trying to solve for b. If you want to solve for b, why don't you multiply by a negative m over t on each side? Multiply by a negative m over t on each side, and you end up getting b equals That's it. That's it. Put the value of m, put the value of t. You have the value 0.75. Get the natural logarithm there. Get the natural logarithm of 0.75. Multiply by the opposite of the ratio m over t. Plug in the m, plug in the t. That is given to us. And we find it. B is 0.0417 kilograms per second when you actually plug that stuff in there. And I got it a little more, my notes got a little more detail on it, but that's essentially all you're doing, guys. You're plugging in the mass. The mass is 0.5. The time is 3.45 seconds. Mass is 0.5. As we said, mass is 0.5 kilograms. T is 3.45 seconds. ln of 0.75. 0.75 is unitless. 0.75 is unitless. Got to make that very clear. If that's kilograms, if that's seconds, B has to be kilograms per second. And it sure is, and it's unitless. It's assumed to be unitless when we're doing this in the process. There's no other way it's going to work for our purposes. I don't want to, I'm not going to pretend to know what other people know in the mathematics, but typically when you're doing with the exponential function, when you've got something on top in the exponent, it has to be set up in such a way that it's unitless. And it's just giving you an idea of what is happening, what kind of proportion is happening, what kind of value is happening with the passage of time or the passage of something else that's going on. So this is where you're going here, guys. If that is the case, and it certainly is the case, we know what B is, what the value B is. Let's have a look. So we're saying, what is the terminal speed of the sphere and what is the distance traveled by the sphere in that? So let me find the terminal speed. We found what B was. It's not really the question that was asked, but it's a question that does have to be answered. It's a question that has to be answered if you're going to get this thing right. So we got B. If we got B, the rest is going to go okay. What do we say way down there? Way to the far right, middle of the board. It says V sub t is equal to mg over b. That is going to give us what we want. Vt is equal to mg over b. And here we go. We got the 0.5. We got the 9.8, 9.81, 9.8. We've got the 0.0417. We're bypassing the units. We know it's going to work out. And indeed it does. At the end of all that, you get 117.53 meters per second. That's pretty big terminal velocity. That thing's moving. No two ways about it. Moving quite fast. I mean, so we've got that. When considering significant figures, we're not gonna nickel and dime that too much. They wanted, rounded to a particular place or 3 significant figures. That rounds up to 118. Typically, that's not what we're worried about, guys. I'm going out of my way the way I'm setting up these problems to not have it happen. That we're going to be worried about that. I worry that you're getting the right answers, that you know what you're doing. All right, so that's that. We know that. That's the terminal velocity. Now, can you tell me? That's it. Simple as that. Can you tell me what is the distance covered when it reaches not terminal velocity, it reaches 1/4. It reaches 1/4 the terminal velocity in 3.45 seconds, I think it was, wasn't it? Yeah, 3.45 seconds. 3.45 seconds, it reaches 1/4 the terminal velocity. In reaching from 0 to 1/4 the terminal velocity, from speed 0 to speed 1/4 the terminal velocity, 1/4 of this is just short of 30. It's like 29.5 or something like that, somewhere in that ballpark. Let me make sure. Yeah, I think it's like 29.5 meters per second, right in that ballpark. So from 0 meters per second to 29.5 meters per second, while that acceleration is taking place, while the whole system is fighting the resistance associated with the viscous fluid, despite the fact that there's a resistance in the viscous fluid, there is an acceleration taking place. How do you know that? It started from 0. It started with 0 velocity, and it went to 1/4 the terminal velocity. 1/4 the terminal velocity is in the ballpark of 29 or 30 meters per second. Okay? About 29.5 meters per second. How far has it gone? That shouldn't be too bad. Okay. So the answer here at the end of the day was, this is going to be the answer. We know the terminal velocity, so let me just make sure I am answering exactly how they want here. What is the terminal speed of the sphere? Okay, the terminal speed is this. That's terminal speed, plain and simple, for A. For B, how far did it go to reach 1/4 that terminal speed? In other words, in 3.45 seconds, how far did it go? So let's take a look at it, guys. Okay, guys, I'm erasing a good amount of stuff here. Luckily, you got the feature that will take us back. Okay. Okay. So how do you want to say this? Well, to handle B, we'll say part B, we remember that V is mg over B. It's a constant. We know what it is. We can plug in everything. When we need to, we plug in as we need to plug in values here, guys. So we're talking about this. Is everybody okay with this logic? Delta X or delta Y, I mean, it's falling through the fluid, so maybe delta Y would be a better way to write it, but who cares? Horse apiece. How far does it fall? We'll say delta X. X or Y or delta X or delta Y, I'll say delta X. It starts from 0, and it goes to a time t. What's the time t? It was the 3.45 seconds that it took to reach 1/4 the terminal velocity. So we got this. What does that mean? It means what it looks like it means. I mean, put V, we just said what V was. V was right here. You know, we worked on this. We did what we did. We got what we got. This is the thing that's kind of running the show here. Mg over B times we got this dt. Well, the rest is calculus. The rest, you know, we're going to do it. We're going to be careful about it. But let's see what we can do here. I mean, the mg you can put outside. You can take the mg over b, put it outside, do the integral here, make it simple for yourself, and then multiply by mg over b at the end. Your call. Basically, the way it's going to go is, at the end of all this, you got, as this goes, I mean, you're going to have dx, or delta x rather, I'm sorry, is going to be mg over b. I'll take him out there. And then, you know, integrate 1 dt, which is just t. Integrate plus a negative e to the negative b over mt dt. That's going to be negative m over b times negative 1, which is just going to be m over b e to the negative b over m dt. Okay, it's a bit of a long dance sometimes to do this. So we got this. So let's plug them in. Let's go, guys. I mean, let's go from t. Let's go from 0 to t. From 0 to t. All right, let's put a t in there. Put a t in there, you got all this. So delta x is going to equal mg over b. We're not going to sweat that too much. And it's going to be this. It's going to be t plus m over b e to the negative b over m t. Put a 0 in here. 0, I mean, we already did the t now. Now we're going to subtract. Put the 0 in here. Here's 0. Put a 0 right here. Oh, that's 0. E to the 0 is 1. That's m over b. Well, you got m over b here. You got M over B right there. I didn't have the other one, so I better not try to get too fancy on this whole thing. But you're looking at something like this at the end of the day, how this whole thing plays out. Plug in all the values, guys. Plug in all the values. M is 0.5. G is this. B is this. We already derived what B was. Times. Okay, sorry, guys, ran out of room a little bit here, so I'm going to have to move the multiplication symbol. Here's the multiplication symbol. All this right here times 3.45 plus M over B, e to the negative, it's the whole thing here. Guys, I'm writing smaller. You might have a harder time seeing it. All you're doing is plugging in the values, guys. The values that you know. I myself not liking how I'm writing it, but you guys know where I'm going. Let's try it again. 345 plus 0.5 over 0.0417 e to the negative 0.0417 over 0.5 times 3.45. Minus all right, guys, it's yeah, I could say it's quite ugly the way I wrote this here, but you could maybe see where I'm going. Here's the big thing, guys. Here's the big thing. Once you've done this and you've brought it once you've done this and you've brought it to here, plug in 0.5, 9.8, 0.0417, 3.45, 0.5, 0.0417, e to the negative 0.0417 over 0.5 times 3.45 minus 0.5 over 0.0417. B is 0.0417. So everywhere you see a B, it's going to be 0.0417. Everywhere you see a T, it's going to be 3.45. Everywhere you see an M, it's going to be 0.5. Plug all that in there, guys. Grind it out. My writing here is pretty horrendous, but I think it's at least legible enough. You know what I'm doing. You're plugging in the value. Once you've done it to here, once you're evaluating between these two, and that's what I've done, then you get down to here. There's nothing else you got to do other than plug in 0.5, 9.8, 0.0417, et cetera, et cetera. 3.45, 0.5, 0.0417, 0.0417, 0.5, 3.417, 0.5, 0.0417. You know that. You know that. Not an issue. Well, once you do it, here's the issue. At the end of all that, what do you get? At the end of all that, in 3.45 seconds, in 3.441 seconds, I'm sorry, 3.45 seconds rather, we've got delta X is 53. It's a big fluid. I mean, it's a big container apparently for this thing to be able to fall this far down. Okay, the mathematics is there for us, and that's what you're getting here for B at the end of all that. So that's what we're looking at. So The other number, the other problem we'd like to do is problem number 41. Problem number 41. An inflated spherical beach ball with a radius of 0.3573 meters and average density of 10.65 kilograms per cubic meter is being held underwater in a pool by Janelle. The density of the water in the pool is 1,000 kilograms per cubic meter. 1,000 kilograms per cubic meter is the density of the water, ladies and gentlemen, and the density of the ball with air and everything else and the plastic and everything else is only 10.65 kilograms per cubic meter, whereas the water, you guys, is 1,000 kilograms per cubic meter. There's definitely a buoyant force. When Janelle releases the ball, it begins to rise to the surface. If the drag coefficient of the ball in the water is 0.470 and the constant upward force on the ball, is 1,875 newtons, what will be the terminal speed of the ball as it rises? Ignore the effects of gravity on the ball. So we're going to ignore the effects of gravity. There is a drag coefficient. There's a buoyant force forcing the ball upward, but there's a drag coefficient. And the faster you go, the more pronounced the drag coefficient is. That's similar to what was going on over here, you guys. Remember when we were doing this whole song and dance of, MA, equals the mg minus bv to do this problem, and how we kept, how we proceeded here. How we said m delta v delta t is going to be mg minus bv, and we kept going. Something similar is going on here, but they're not giving us mg as that being an issue. We're ignoring the force of gravity on the ball that's also helping the drag. The drag that's associated on the ball is being helped by gravity. Gravity and the drag are stopping the ball or preventing the ball, are hampering the motion of the ball to go upward. We're not going to worry about gravity, just the drag that's associated with the ball going upward. That's the only thing we're going to worry about. Whereas gravity would also factor in, and gravity would help. Gravity would help the drag to slow the ball down even more. But that's not happening here. We're just worried about how much drag is going on, and then there's a constant force pushing it upward. So it's similar to this, though somewhat different. So let's look at problem number 41 in regard to something like this and see where it's going to go, you guys. So let's see where it's going to go, you guys. Let's see what we can say here. Now they've gone into this a bit. They give us in the book how this would have to proceed and how we'll have to do something like this. So I guess we can. There's a number of ways this can be looked at, but I think they're trying to make this a little easier to look at. We will look at. Let's just look at it. I mean, from the book, we can see that the amount of drag force is 1/2 times c rho mass density area v squared. That's for terminal velocity. So if you want to find terminal velocity, we know that this is kind of taking us back a little bit to what we did just now, in fact. Look at something like this. So if that's the case, when we do the force here, they're saying don't associate with ignore the force of gravity. It's kind of a little bit of a different situation here, guys. We're going to do something like this. If you're going to look at it, like I said, if I could just find this really quickly, for some reason, I think it just needs to be talked about a little bit. If I don't find it, it's definitely in the book, but for the life of me here, there we go. So they talk about this a little bit. The discussion here is not exactly the best, but not too bad. Okay, so they're saying basically what is in the Katz book on page on page 165. We see what we got here. They're saying here we write all these factors: object shape, density of the medium, rho. So rho is the density of the medium, and the density of the medium, rho, is water. Rho would be the mass density of the water in that equation that I gave up there, you guys. Rho is the density. Objects perpendicular cross-sectional area A and speed V into one neat equation. Well, the cross-sectional area is rather fascinating in its own right. The drag coefficient is a unitless quantity. That's C. So C is a unitless quantity. Capital C is a unitless quantity. Rho is the density of the medium in which the ball finds itself. In this case, water. That's 1,000 kilograms per cubic meter. A is the exposure in terms of area, maximum cross-sectional area of the ball. And we're going to have to talk about that a little bit. And V is the speed that is attained there. So let's see how this all plays out. What they're saying here is, what will be the terminal speed of the ball as it rises? Ignore that. Well, to find the terminal speed, there is, as we just said, guys, there's sort of in V into one neat equation. So let's see exactly where it's going to go here, guys. The way it's set up, we have that here. We're going to say that the weight of the ball, now they said ignore the weight. Well, yeah, ignore the weight in some sense, but you got to understand the fact that there's drag force and there's also the weight of the ball. So let's see somewhere where it's going to go, you guys. They could say it in a number of ways. It's a little deceptive how they say worry about, don't worry about the mass of the ball. Well, yeah, I mean, I don't know about that. What will be the terminal speed? Ignore the effects of gravity on the ball. Well, I'm not sure that you can do that, but let's kind of see what they can say here regarding this. This is mg is the weight of the ball, and that's going to be equal to this. That will happen when you got a terminal speed. Let's kind of go there. I think what they're trying to say is, don't put in the weight of the ball when you're. I'm not sure. I'm not going to lie to you guys. I think we can just arrive at this conclusion independent of the effects of weight of the ball. That's probably where they got that to begin with. But at the end of the day, the ball does have weight. It is being pulled down. What happens is the weight of the ball being pulled down, and the terminal speed of the ball. The terminal speed of the ball is a constant speed. What does that mean? That means the weight of the ball and see here what they're trying to say. No. This is why actually. Let me take that back. We're not going to worry about. We're still not going to worry about the weight of the ball. Yeah. Now you're going to ask me, Malus, you said we're not going to worry about the weight of the ball, and now you just wrote the weight of the ball. Yeah, I did write the weight of the ball there, but I'm not worried about how much the ball weighs. I'm ignoring the fact that the ball has weight. The weight is, we're going to ignore the weight of the ball. Then why did I write down mg? Because the buoyant force is mg. If you immerse that ball completely in water, then the entire volume of that ball times the mass density, there's air in there and there's the plastic and all that stuff. They'll just say the whole ball, meaning the air that's in there too. If you immerse that entire ball, its entire volume, If you immerse that ball, its entire volume, in water, immerse it completely in water, then the volume of that ball times the mass density of the ball. The volume of that ball times the mass density of the ball will tell you the mass of the ball. Multiplied by G is the weight of the ball. The buoyant force, according to Archimedes, is equal. The buoyant force, according to Archimedes, is equal not to the mass of the ball, but equal to the mass of the fluid that is being displaced. So in other words, if I found the volume of the ball, start this kind of over, I guess you could say, guys. This mass right here is not the mass of the ball. We're not worried about the mass of the ball. We're worried about the mass of the water that was displaced. In other words, this M equals the mass of the H2O that was displaced. So mg is mass of the water that was displaced. So if I find the volume of that beach ball and multiply the volume of the beach ball times the mass density of water, according to Archimedes, that's the buoyant force that's firing up there. The buoyant force, mg, which is a better way to write it. And in my notes, I was a little too cavalier about the whole thing. So in the written notes, just make sure that this M right here, absolutely, you write it like this, times G, that buoyant force firing upward, buoyant force firing upward, which is mass of the water, times G, which is equal to the mass density of water times volume of the ball. That's where it gets a little confusing. Mass density of the water times the mass density of the water times the volume of water that's displaced, which is equal to the volume of the ball, times G, will give you the buoyant force. Right here, you guys, the buoyant force is going to equal to the drag force. What does that mean? The buoyant force is firing the ball upward. The drag force is fighting it with exact equal force at the point of terminal velocity. When the velocity is at terminal velocity, the velocity is at a constant speed. Terminal velocity means the speed of the ball is going at a constant speed, which means that the forces balance out. The buoyant force and the drag force balance out. And that's where you want to go with this. That's where you want to go with this. This is 1/2 C rho of the medium. Okay. We'll get there in a second. That's the rho of the H2O. Area V squared. Let's see how they want to talk about it. But this is what's going on. I should have been a little more specific in my initial presentation. That's completely my fault. That's completely my fault. But there's how you go. This is what you're looking at. That's my fault. My notes are a little, then I jump into it a little bit later with the notes. But I think that's what I had done a little bit in the notes here is likely a little more confusing than it's helpful. Then we start putting in the actual, this stuff gets mentioned a little bit later in the notes. Should have been mentioned up front. So it's an interesting situation in that regard. This FG really should be it's the FG it's the F sub G of the water that is displaced. You know, it's the F sub G of the water that is displaced. So, well, FD equals FD. That's obviously true, but it's a better way to write it. Better way to write it. And that's what I've been writing here. That's essentially the argument, you guys. This buoyant force is going up. The drag force is going down. F sub D and F sub B are equal and opposite to each other. If that's the case, let's see what we can do here. Now, again, the way I did it, I bypassed writing all this stuff down. I wrote this, which is true as long as you know what the M is. The M is not the mass of the ball, as I was erroneously speaking earlier. So please regard that as a correction. I mean, that's the mass of the water that the volume of the ball displaces. That's the mass of the water that the volume of the ball displaces. So there's a lot going on here, guys. What does that mean? Means a lot. I mean, it means a whole lot. I mean, what you can say here is that mass of the water, this could be rho H2O times the volume, and we can kind of take it from there. So let's see exactly how I wrote it. I just want to I think, guys, that's the buoyant force. I got to feel they may. I'm not incredibly confident with this thing, the way they got it all set up. I'm simply not agreeing with my own notes here right now at this moment. Let me just, this to me is the way you got to go. For some reason, when I had looked at it, it might have been something different than this. I am having a really hard time believing this. Let me think here. Okay, guys, let me look this up really quickly. I am not if I'm bold enough to say it, either they did it wrong or I did it wrong. But let me 0.46. Yeah, they're giving that answer. They're giving the answer. They're giving the answer that I'm giving when I first did it. So ignore the effects of gravity on the ball. The constant upward force is this. The density of the water in the pool is this. When Janelle rises the ball, it rises to the surface. The drag coefficient is this. The constant upward force is this. Well, if the upward force is this, how are you going to actually get it to go to that? Yeah, I mean, I'm giving the same answer the book's giving, but for some reason, it just doesn't. This is not something I'm having a hard time believing this, to be honest with you. There's the buoyant force and the drag force. I am going to think about how to do this, guys. Let me talk about this a little bit. They're saying this. My look at it is different. As I'm looking at this right here, we're ignoring that. I'm saying that the buoyant force has to be equal to, I'm gonna stay with stay with this, I think, a little bit on this, and let me see what I can say here. This is rho times V of the beach ball, and I don't know. I'm gonna keep going with this a little bit. I'm gonna keep going along these lines for some reason, guys. The weight of the water is the buoyant force. They are saying what is going on with this. MH2O is rho H2O times the volume times G. That's the buoyant force. We got 1/2 C rho H2O AV squared. The rho H2O gets out of there. Yeah, it's just something we're going to have to figure this out, guys. I'm thinking the way they got it solved, I'm having a hard time believing it, to be honest with you. The drag force, force of gravity for terminal velocity, constant upward force. It's just hard to believe this stuff. I mean, the way I think the way this is fine. If they're saying there's a constant force, I'm going to take this. And say that's the 18 that they're saying that's the constant force here. I wonder if we can actually get the right answer that way too. I'm going to leave it like this. Let me think, guys, quickly on this. I could say that they're saying it's going to be that. I'm thinking 0.3573 meters, 4/3 pi r cubed times the density. I'm wondering if it's going to be doing that the 18 business that we're just talking about. Let me just see here. I got a feeling here. Perhaps they did something wrong. It just the numbers just don't seem to be working, guys. I'm going to take the 0.3573 meters. 0.3573 meters. I am going to cube it. I'm going to multiply by pi. And I'm going to multiply that by 4/3. That's that. If the drag coefficient of the ball in the water is this, and the constant upward force on the ball is this, what would be? Even here the numbers aren't really what I think they should be, to be completely honest with you. But then again, let's keep going. Yeah, it's okay. I think I got it. Yeah, I'm agreeing with that. They said it's 18.7, 1875 times, let me just see something here, guys. Right on the mark, guys. Yeah, okay. My gut's right on this one. Sorry for the whole song and dance here. When you actually, okay, this is how to explain this one. Yeah, this looks okay. This is not bad. This right here, see what I can do. This is the buoyant force. That's big. This is pretty big time stuff, guys. If you go, okay, this is what I thought. Sorry about this. Some of this stuff doesn't. Let me refrain from judgment. There may have been a mistake in the key. So hopefully let's fix it. I mean. Let's not go there yet. I mean, I got a feeling it might be fine. It might work out. I'll be honest with you right now as I speak. I don't want to be too bold, but I'm going to have a hard time thinking the key's right. Depends how the question's being asked. Perhaps they should have given a little more information, but this is big. I just told you the buoyant force on that ball that is weightless. We're going to pretend the ball has no weight. That's why I think the answer key in the book. I think look, man, these guys do tremendous work. They do great work. On occasion, I'm going to make a mistake. They're going to make a mistake. We're all going to make mistakes sometimes. They may have made one here. So let's kind of correct it. If you reach terminal velocity, the drag force is equal to the buoyant force. What is the buoyant force? They said don't worry about the weight of the ball. The way they got it solved in the key, I think they do worry about the weight of the ball, and they shouldn't have. So I think they're wrong, the answer they gave. If that's the case, and that can happen to anybody, if you're doing thousands of problems, guys, on occasion you can get something wrong. That's a human thing. The drag force is equal to the buoyant force, which means there's just a constant velocity as it goes up. That constant velocity is the drag velocity. That constant velocity is the terminal velocity. When the drag and the buoyant force are equal and opposite to each other, either there's no motion whatsoever or there's motion at a constant speed. Motion at a constant speed, it cannot go any faster when the drag force pulling down and the buoyant force are equal and opposite to each other. They cancel each other out. When the drag force and the buoyant force are equal and opposite to each other, you've reached terminal velocity. The drag force is given by this. And the buoyant force is given by this, but I said you better be careful how you say it. The drag force is the amount of pull down. The buoyant force is the amount of push up. We don't worry about this very light ball and its mass. We don't worry about the mass and force of gravity of this very light ball. We can worry about its mass, I guess, but we don't worry about the weight of the ball because it's very light. However, that beach ball, when it's immersed in water, displaces an amount of water equal to the volume of the beach ball. The volume of the beach ball is the volume of the water that's displaced. The volume of the water times the volume of the beach ball, which displaces the water. The volume of the beach ball times the density of water will tell you the mass of water that was displaced. Times G will tell you the weight of the water that was displaced. That is the buoyant force. Mass of the water times G, which is what I did over here. This right here, rho H2O times V of the ball is the mass of the water. And this is G. So this guy right here, what is that? Well, it's this. It's rho H2O times the volume of the ball. The volume of the ball is 4/3 pi r cubed. Really? The rho of water times the volume of the ball that displaces this, which the volume of the ball is the same as the volume of the water that is displaced. volume of the ball is the volume of the water displaced times the density of water. Volume of water displaced, which is equal to the volume of the ball, times the density of water is the mass of the water displaced. Times G is going to equal 1/2 C rho H2O AV squared. This is pretty fascinating stuff. This is 1,000. That right there is 1,000 kilograms per cubic meter. This is 4/3. This is pi. And this is 0.3573, I think. Let me forgive me, guys, 0.3573 meters. Cubed. Times G. They used what Dr. Katz uses in her book. Not 9.8, they use 9.81. Ladies and gentlemen, if you work this whole thing out, you get really close to the claim they're making. They claimed that it's 1,875 newtons. It's 1,875 newtons. This is 1,875 newtons, and it's equal to this. I am not sure. Again, I'm not going to make a final judgment on that, and I'm likely. We don't frequently go. This is not a problem you're frequently going to see at this level. I haven't used drag force too much, but it's good mathematics. What I just wrote is true. What I just wrote is true, and what they just wrote is true, because they gave this answer right here: 1,000 times 4/3 times pi times the quantity 3 times the quantity. So 1,000 times 4/3 times pi times the quantity 0.3573 cubed times 9.81, that's 1,875, or pretty darn close to it. So that's 1,875, and I'm not sure. I'm not sure what the key was thinking. The key might have this wrong. They probably did something careless happened, and that can happen to anybody. But that's big. So this thing is 1875 or pretty close to it. What I got when I did it, let me see. I got 1874.37. Man, it's pretty darn close. I mean, if you do the right round offs and stuff, 1874.37. They say 1875. Yeah, this is it. This is a logic. There's nothing wrong with this logic, guys. Nothing wrong with it. So if that's the case, why don't you keep it there? And why don't you look at the other stuff and actually get what's going to happen? So then when you look at it, okay, so let's... All right, guys, forgive me. I'm kind of doing this cold because I'm going against my own notes. My own notes were similar to the notes given by the book. I should have questioned it. Watch me be wrong again, but I don't think so. I'm not going to be given this stuff. Drag problems, I don't think I'm going to be given a drag problem on any of the exams. And if I do, it should be a lot more straightforward than this, but unlikely it's going to be given on any of the exams. But this is still good for us to know how to do. So let me go away from the notes. Let's just talk about this. They're saying about 1875 right here. That whole thing is 1875. I'm saying it's 1874 point something. I don't think that's the big problem right here. That's the upward force, you guys. That's the upward force, and it's going to be equal to the drag. Let's see where this ends. Maybe it ends the same place. I find that very hard to believe that their answer key is right. And I find it hard to believe that I'm right, having followed that answer key. Rho H2O AV squared. Okay, some of this stuff we're going to have to visualize what's the biggest surface area that's being encountered there, and we'll kind of take it from there. Let's go pi r squared. Let's say this. The surface area that's straight out on it, let's say. Let's do a whole bunch of stuff here. Let's multiply by 2. Multiply by 2. Divide by C rho H2O rho H2OA. Square root that, and that's going to be V, and that's going to be V terminal. VT is the square root of 2 times this, and again, I'm spotting them. They're right on this one, or they're pretty darn close to right on this one. When you do this, you get 36, 37, 3750 in the ballpark of 3750 here. And let's see what else. They told us that we're going to assume the other stuff is on the mark. If the drag coefficient of the ball in the water is 0.470, 0.470, row of water is 1,000. This should be interesting. And the area of exposure, and that's pretty interesting on that one. So what they're saying for that is, see where they got the A here, guys. It's unitless. C is found by experimentation. I was just looking at it, and for the life of me, I cannot find it here. I just want to confirm what they had said here for the terminal speed. One additional factor, the object shape affects the drag force on an object moving through air at high speed. For example, car designers wish to reduce all that. You are looking at, for some reason here, I was just looking at it, and for the life of me, I'm not able to find it. The area, find the cross-sectional area of each object for the surface perpendicular. Find the cross-sectional area of each object for the surface perpendicular to the direction of motion. Therefore, if it's this, you guys, if it's a ball, a beach ball, I want to find what's the perpendicular. Well, the perpendicular, I understand that, this is important. The area of a sphere is 4 pi r squared. The area of half a sphere, because I'm only getting hit by half a sphere. Here's the area of a whole sphere. The area of a whole sphere is 4 pi r squared. The area of half a sphere is 2 pi r squared. Yeah, true. That's not what they're talking about. They talk about what's being exposed. They're talking about the perpendicular area of exposure. Bam, perpendicular, perpendicular, perpendicular. And that's as though it's flat. And that's pi r squared. And that's pi r squared. So you put a pi r squared here. You put pi r squared, and we said, what do we say that was? That one was 0.3573. 3573. And that's that. Wow. Interesting. Squared the whole thing. Let's see where it's going to go. I think the book made a mistake. And I think I made a mistake following the book. Let's see what we got. So there's plenty of mistakes to go around sometimes. Let's take 3750 And let's just go here. Let's just go. 1,000 times this is 40. Is 470. Um, 470 divided by, got this. Okay, let me just do this, guys. Without talking about it, you guys can see how to do it. Same way you would do any problem like this. Okay, let me just make sure that I'm on the mark here, guys. I do not want to see this go bad again. All right, you've got this. You got this and divided by this entire product. Square root that. All right. This is it. For a rough, again, I would have used a little different number here because my answer was a little different than theirs. I had 1,474.4 something or 0.3 something, 1474 point something, 1474.4 or 0.3 or something like that. They got 1475 and they kind of left it at that. I'm getting this, and this is more believable. I am going to stick with this. I'll bring this up to my contact person. And I think it's just something to watch out for, guys. We'll look out for that. That needs to be corrected. That's not right. The point, they got 0.46 meters per second. I'm almost wondering if they just ignored the 4 that was there. But their setup on it, the mathematics is, it's not right. It's just simply not right. Let me just make sure before I start throwing stones here all over the place. Let me make sure I'm not making an accusation here that's not correct. They got 0.460 meters per second. That is not according to the logic. That doesn't work. That doesn't work. This does. This is true. So, did not expect that. But please, look at it. Looks neat. Follow that argument. Follow that argument. At no point does the mass of the air and G come involved here because that would bring it down even further. Perhaps they're getting, I don't know where they're getting that from. They solved the problem using this, but we said at the very beginning that you're not supposed to be using that. They said that at the very beginning, and then I started going along this erroneous track, and then I caught myself, and we were able to finish it. That's what it should be. All right, that is that. Let me see if 67 goes smoother. It's a great problem, guys. It's a great problem. Learning from this is very important. Very important. So, for 67, it's a little bit of a long problem in its own right, but we'll see here. I might have to take a little look at it. But for problem number 67, a block of mass capital M is placed on a frictionless plane. The plane is inclined at an angle theta, and the block is a distance d from its end. Of course, we would expect the block to slip down the plane. It's a frictionless plane, you guys. Even though the block is mass capital M, it's a frictionless plane. We expect it to slide down the plane, guys. That's what they're telling us. Suppose we revolve the incline around the vertical axis shown instead. At what period of revolution will the block remain in place on the plane? So this is neat. This is going to get us into the suitcase problem that we'll do some other time. But right now, let's just do this. So let's do problem number 67. So basically, guys, in the notes for problem number 41, ignore the notes till I put a correction up there, or just ignore it, period, and look at my video on that. I'll mention that as well, but I think I'm going to have to post this as a correction for 41. So that should be done, and that will be done at some point. So watch out for that. Do what I showed up here for problem number 41. Obviously, I was trying to think at the same time that I was correcting it, so and I've got a hard time thinking to begin with, and while I'm trying to correct something, I really have a hard time thinking. But anyway, all jokes aside, we do have it solved up there for you. I hope it helps you out. All right, they are saying that there is this pole right here, and they're saying there's a slice of something right here. There's a block right here, mass capital M. It's on a frictionless surface, and we got to figure out what's going on here. It's a distance d to get up to here, and where you're going to put it to the middle of to the center of mass or whatever. We'll see how it works out. But if this thing right here is d, and this thing right here is theta, and the weight goes down this way, mg, and theta, 90 minus theta, once again, ladies and gentlemen, that's theta. This is the slide down component, mg sine theta. This is mg cosine theta. There's a normal force here, but it doesn't really amount to anything, guys, because there's no friction. So we can't really do much about it. This is mg. This is this guy, but this is the slide down component. That's important. This slide down guy wants to go down this way. You got to rotate it in such a way that this thing wants to fire out the other way. Well, there's the centripetal force that is pulling this guy this way to hold him in place, Fc. There's an Fx, there's an Fcx right here. If this is theta, that right there, that's also theta. These are two parallel lines. Parallel line, these two lines are parallel to each other. Theta equals theta. Alternate interior angles are congruent. This is F sub Cx, this is F sub C. If this distance is d, this distance is d cosine theta. This is the length of the arm as you're swinging this around. F sub C is mv squared over r. mv squared over d cosine theta. The lever arm whipping around, and we'll talk about the centripetal force. We already have talked about the centripetal force. This guy d cosine theta is the length of the arm right here. Should use something different color maybe. That's the length of the arm right there, and that's d cosine theta. This and this, as we said, that's theta. That's theta. This is theta. They're alternate interior angles. They're congruent. So, I mean, there's a lot going on here, guys. So what do you want to say? Well, I just said this, which is pretty important for this guy. Fcx is equal to mv squared. Let's have a look here. Let's really have a look here. Right. Let's see what we got here. This component right here, you guys, I want this component right here, this Fcx, I want it to be as strong as the slide down component. Fcx is going to have to be, I want this tendency, this guy's centripetal force, holding this guy in place, FCX, to be as strong as mg sine theta. So FCX is going to be as strong as mg sine theta. And what is this guy? Well, he's not as long as this one. This is, you're talking about FC being this. You're talking about FCX being this. That's theta. This FCX is FC cosine. That's the hypotenuse. This guy's the hypotenuse. Don't make a mistake, guys. This big one right here is the hypotenuse. That's the leg. Therefore, this guy's the leg. FCX is FC cosine theta. So you got this. So this FCX is going to be this guy. Times, didn't we say, we said FCX is FC cosine theta. FCX is FC cosine theta. Believe it or not, I know this is a bigger number, but a big number on the bottom gives you a smaller answer. D cosine theta is small. D is bigger than D cosine theta. Big on the bottom means this whole thing is small. We basically looked at it by saying the way down, this thing right here has got to be as strong as this guy. We got to here. Multiply by D over M on each side. Multiply by D over M on each side. We got this. Is the circumference divided by the period equal to velocity? Is that the same as 2 pi r over the period? The total distance all the way around divided by the time it takes to go all the way around is equal to v. Sounds good to me. Wherever you see a v, put that. 2 pi r over t. GD so we got that. Well, keep doing it. Square the 2, square the pi, square the r. DG, DG, GD, DG, who cares? I mean, that's as long as it's there. Get the reciprocal of both sides. Flip both, get the reciprocal of both sides and then multiply by 4 pi squared r squared on each side. T squared equals, right? Flip it upside down. You get 4 pi squared r squared over GD sine theta. Not bad. Okay. You guys can always turn this back. Okay. Yeah, it is what it is what it is. Didn't we say that the radius is this guy? This is the radius. Now we got to be really careful here. We got to be extremely careful here, I think. Yeah, the radius does, guys, why does the radius have to be what I'm about to say it is? Because this guy, this is your circle. This is your circle. Your circle happens right here. That's D. This is theta right here, right? D, here's theta. This is D cosine theta. That's your radius. That's your radius, ladies and gentlemen. That's the radius right here. That's D cosine theta. So you're going to put it for here, you're going to go for it and go that way. So let's see what we got here. We've got t squared equals 4 pi squared, r squared. What's r squared? D cosine theta squared over GD over GD sine theta. Yeah. True enough. Let's just make sure I got it down right. Yeah, it looks good to me. 4 pi squared times the quantity d cosine theta squared over G over GD sine theta. Okay. What's going to happen is you're going to have d squared cosine squared theta over GD sine theta. The d's cancel. The d's cancel, and you've got four pi squared. Let's see what we got here. 4 pi squared, okay, as we said, the d's cancel. D cosine squared theta over G sine theta. Square root both sides, my friend. My friends, square root both sides. Square root of 4 is 2. Square root of pi squared is pi. Square root of d is square root of d. Square root of, square root of d is square root of d times the cosine of theta over the square root of g they write it a little different. I mean, there's different ways you can write it, but what I see here, guys, is what they do is they say, okay, let me put this. You can kind of say this. You can say square root of d is equal to d divided by the square root of d. For some reason, I don't know why you'd want to put that. I don't know why you'd put it like that. So this comes, the square root of d right here, you can multiply by you can multiply this fraction by square root of d divided by square root of d. Multiply this fraction by the fraction square root of d over square root of d, and you end up getting this. That's the way they kind of wrote it. That doesn't matter. I mean, we know what we're doing. Multiply by square root of d on top and multiply by square root of d on the bottom, and you end up getting this, maybe a little easier to look at, apparently. Well, there's less square roots there. There's less square roots, I guess you could say. I don't know, you can argue this a whole bunch of ways, actually, but sine theta. So what we got here is the end of all of that. I think this is the way they gave it in the book. I'm not sure it's the best way to write it, but it's certainly not a bad way to write it. And it's probably fine. I mean, it should be fine. A lot of times you don't even want a radical in the denominator. You could kind of argue, if you played the cards right, guys, this is it. I mean, this is the answer. This is the answer they gave. There's nothing wrong with this. There's nothing wrong with this. There's your answer. There's your answer. It's the same as this answer. Mathematically speaking, these are identical. Technically, they don't like square roots in the denominator. You'd have to rationalize this denominator. Let's not open that can of worms. Okay? But that's where it's coming from. That's where it's coming from. So what do we got here? Yeah, capital T, the period, is 2 pi d cosine theta over the square root of the product, dg sine theta. And that's exactly the same as this right here, you guys. Works fine either way. All right, guys, thank you. And we will talk to you soon.